start with an ion. You fire a laser at it, you get some electrons, and you end up here? Like, how did we get here? How can you start with a gas, push it around in wacky ways, and end up with a graph based on a slice, based on a reconstruction, based on an image, based on a detection? What's going on? Well, that's what we'll get over in this video. This actual machine built for actual chemistry research and how it works. But first, we need to get our molecules ready with the... Okay, I don't really have a budget to model the full machine, so we'll have to do it with boxes. I'm so sorry. The idea behind the experiment is pretty simple. We start with some molecules in an ampule, then we connect it to our machinery, which sucks it up in the form of a gas, and that's where it begins, first with the ionization. Okay, so for the rest of the experiment we'll need our particles to have net charge, or in other words, we'd like them to be ions. How would we ionize them? Well, a simple-ish way would be just turn our gas into plasma. Basically, plasma is just an ionized gas and... whoops. Okay, it's not really an ionized gas, but the states of matter is a story for another time. And so for the sake of the experiment, we mostly only care about it being ionized, so trust me, it's good enough in this case. That's why the highlight of this chamber really is gas molecules in, ions out. Now next there is... acceleration. So we have an anion, a molecule with an extra electron. Why do we need that extra electron? Well, it's because if you shine a laser at it, it can easily detach from the ion. And once you take all of these electrons out and measure them, we get random garbage. That's a bit odd. This is meant to be actually something different, not random garbage. Well, would you have to realize that the molecules we put in there are a mixture, and the process of plasma creates even more funky molecules. So this output is the output of all of the different ions combined. We want them separated though. And so that's why we need to figure out a way to separate them somehow. And wouldn't you know it, it just so happens that the by-effect of our ions being negative is the fact that they will in some way interact with the electric field. So if we apply an electric field to them, they will accelerate. And this is important. That's because the higher the charge, the quicker they will accelerate. Charge tells you how much something is affected by the electric field. So if our molecule leaves plasma chamber with a lot of net charge, then it will accelerate quickly. If it however leaves with a little bit of net charge, it will accelerate slowly. Kind of. That's because yes, more charge means more acceleration, but there is another property which makes the acceleration different between molecules, and that's the mass. That's because if our high charge particle ends up extremely massive and our low charge particle ends up with a little bit of mass, then the velocities can switch. And now we can use this property to measure the charge to mass ratio. How? Well, if you start with the molecules at the start, apply the field, then they will accelerate in a certain way. Now, after a certain amount of time, we stop and measure how far they went. Now that tells us how much they accelerated, and that in turn tells us how high their charge to mass ratio is. Or at least it would, if not for the fact that it actually assumes something. It assumes that they all go in parallel. That's because if they were not going in parallel, then this angle will actually screw up the distance. So how do we fix that? Well, that's simple. No, I'm just kidding. It's not. It's called an Einzellens, But the point is, you can just take all of these ions traveling in different places and then make them go all in parallel. Then you can also use it to focus them onto a single point, but we'll get to that later. A kind of crucial thing to remember here is that these distances are just there for the sake of visualization. And in reality, you want these two to be as short as possible and this one to be as long as possible. That's because only if ions travel in parallel can you get the charge to mass ratio and separate them by it. Then after that, the other lens focuses them onto a point, and then past that point it hits the detector, and there. That's all for our setup. And I know it was a real awful lot, so let's go through it all again, this time in a bit more strict and linear way. So first, we start with our molecules as a gas. Then we turn that gas into plasma, which results in the molecules switching to ions. We need them to be ions because we want them to accelerate when an electric field is applied. So then we align them using an Einzellens, and now the molecules with higher charge to mass ratio will end up further forward. And that's why this part of the experiment actually requires a fair bit of length. The more distance they travel at different velocities, the higher the separation between them, which we'd like because then we Einzellens them back into a single point and let them hit a detector at the back. Now, this detector just detects the intensity of ions, which means that as ions pass this point, this is what the output of the detector looks like. There. Now based on this data, you can figure out which molecules are passing when, simply because we know that molecules with higher charge to mass are here and lower charge to mass are here. Simple. Okay, so we've already gone through a bunch of different steps and a lot of problems, but what happens now? Well, now is a bit relative because all of this, every single step we've done so far, was just made so that we get ions going past this specific point. And so now that we know when and which are going through it, all of this was basically the equivalent of washing glassware before the actual experiment. And now it's time for us to fire a laser at them. Why? Okay, well, first things first, you don't need a justification to fire a laser at an ion or anything really, but in this specific case there is actually something we'd like to measure, and in order to understand that we'll have to take a brief look at light. Oh no, wait, we won't have to, I already did that in the quantum field theory videos, but to recap, when you hit a molecule with a photon, or in other words, light, this photon has some amount of radiant energy, inversely proportional to the wavelength. So here's light with low energy. Here's us increasing the energy, and great. So what happens when this light hits our molecule? Well, just like if you have two balls, if one of them has a lot of kinetic energy, then when they collide, what we get is the transfer of energy. Simple as it could be. The higher the kinetic energy in, the higher the kinetic energy out, except there is a pickle. You see, our electron is sticking to our molecule, and in physics you don't really have anything for free, and so there has to be a force keeping it in place, which means a more accurate model would be our ball, with the second one being held in place by a kind of force field. Now if you hit our ball with the first one, it won't budge, the force field is holding strong. And so if you'd like to push the ball, what we actually need to do is get more energy and hit it again and again until it breaks. And the same thing goes for our ions. I always like to visualize it with these two bars. The right bar will represent the energy of the laser, the left purple bar represents the energy required to knock an electron off, and the red bar, which will soon appear on top, will represent the energy of the electron leaving it. So as we increase the light energy, nothing happens initially, because our energy isn't high enough to break the electron away, but then, eventually, we get past this point, and electrons start leaving. Now these electrons aren't leaving a single ion, and right here I'm showcasing more of what happens as our experiment goes on with lots of ions, but the point still stands. As we increase the energy, eventually the electrons start leaving, and then the higher the light energy, the higher the kinetic energy of our electrons, and the quicker they go. Why does that matter? Well, imagine the same animation except with one slight difference. Instead of visualizing them one by one like that, I visualize them with all electrons at once, like this. Now what will the energy mean in this case? Well, it will mean how quickly these electrons are moving away from our molecule. So for example, here's the low energy electrons, and here's the high energy electrons. Now you can see that after 2 seconds of simulation, here's the low energy, and here's the high energy electrons. So the size of the sphere goes up or down based on the energy. But this is still an experiment, so let's get back to reality for a second. Because after all, this is still an experiment, so what are we doing? Well, what we're doing is we're firing laser at ions. We get all the electrons detached, we push them towards another detector, and now as they go, they all expand according to their velocity, and when they land on the detector, this is what they look like. Isn't that quite something? Now we can see it with multiple spheres. It works in the same way, and there. That's our output. Honestly, I gotta say the geometry notes I did for this are quite lovely, so I'm just gonna do one more just for the sake of visualizing it. And there. And now after that, we're finally done. That is the full physical setup of the experiment. The full machine. And now we can ask, I know it's comically late in the video to be asking that, but now we can finally ask, what are we even measuring? So yes, this is the part of the experiment where I explain the electron affinity, and I'd just like to take a second to pause here because holy shit, this image on the left is what I just made in Blender, but this image on the right, that's actual electrons. I just want you to reflect on that fact for a second, okay? This image on the right, this heat map, is actual, real electrons hitting the real detector. Here's a picture, and the video. Isn't that awesome? But the point I'm trying to make here is that when you take a look at these pictures, this is how we actually get them. But what causes these electrons to be in different places? Well, that's the electron affinity, or in other words, this purple bar. This electron affinity tells you how much energy you need to detach the electron. But get this, there can be more than one level. And so if we've got 3 levels like this, then here's what the detachment would look like on different energies. First, we have the low energy. Second, there is the higher energy. Third, there is the highest energy. And then finally, the crazy high energy. Cool. No wait, crazy cool is what I actually meant to say. But then there is the more interesting question. That's because with this experiment, these levels is precisely what we're trying to figure out. So a much better example would be, let's say that we don't actually know the levels. And let's say that we give it some energy and we get back a sphere like this. How do we get the levels back based on those spheres? The idea should be simple enough, right? I mean, based on how large these spheres get, you should get the electron affinity. Right? Well, it would be if not for 2 facts. First of all, take a look at this sphere. It looks fine, right? I mean, it seems like you could just get the energy based on it. If not for one problem. Here's the same sphere at lower energy. You can see there's actually 2 spheres, and that's because velocity squared is actually proportional to the energy. So the difference in velocities will be a square root, which means that at really high energy, the difference won't be noticeable at all. And that's why you need to be careful with the energies. You want to make sure that the sphere you're seeing is actually a singular sphere. The simple way to solve this would be to just obviously measure everything at many more levels, which honestly shouldn't be a problem. I mean, scientists love data, and so just doing more measurements is, well, let's just say they don't quite mind.
Well, hang on. You're not the one who had to spend 6 hours in the lab getting one set of data.
6 hours? I spent 18 hours on just these last animations.
You mean the animations you've copied from my research diagrams?
Oh, so you think it's easy, huh? Easy making a video. How about you give it a try, okay?
Okay then. Hi. I'm a master's chemistry student doing research in this area, which is chemical physics. That's my hand right there. So I'm going to try and explain what we can actually do with this image that we get from the detector. Firstly, we need to solve a problem. We've squished a 3D sphere into a 2D circle. But what that means is we've lost a dimension, and that means we've lost information. If you pick a point on our 2D image, like here for example, that point can mean any point along this line in our 3D distribution. So how do we fix this? Well, thankfully, the distribution pattern made by all these electrons in different directions actually has symmetry around this axis in the middle, which is because our photon is polarized this way. This means that we can actually reconstruct our 3D spheres if we use a bunch of boring maths. Thankfully, we're spared from the horrors of Legendre polynomials and basis functions because someone on the internet has done all the work for us and written a script that applies the maths to the data. So all I need to do is a bit of coding that makes this work for my data, and we get more circles? Well, okay, these circles are clearly different. What the code has done is it's guessed what the spheres would look like from our 2D image, and effectively taken a slice through that 3D sphere. And the image now has all the data we need. The intensity at any radius can be converted into the intensity at each kinetic energy, if we remember our relationship from before. And of course, we also get the angular distribution of our electron spheres in terms of the beta parameters. Wait. Make it. You haven't explained this bit yet?
I was busy with other stuff. More videos to make.
Okay, let's get quantum. Electrons exist in orbitals. In an atom, these are well-defined atomic orbitals, which have specific shapes that tell us where the electron is likely to be found. These shapes are defined in terms of the angular momentum quantum number, or L value, which chemists usually call s orbitals, p orbitals, d, and so on. Now, when the photon interacts with our anion and ejects the electron, the L value of the electron has to go up or down by 1, which is just because quantum. So this means that if the electron starts in a p orbital, which is an L value of 1, then it needs to get ejected in a wave that's s-like or d-like, so an L value of 0 or 2. That doesn't really look like a d orbital. Well, for the sake of not smashing our heads against a wall for 3 hours, let's just say it's close enough and not worry about the quantum mechanics here. So we've defined the shapes of our spheres. Certain ejection directions are more likely than others based on what orbital the electron was in before it got ejected. But it's also based on the energy we've given to the electron using the laser. See, there's a barrier we have to overcome to get to our D-like wave because it's considered higher energy. If you increase our energy slowly, eventually you get past that barrier and you get a D shape. Easy peasy. Actually, no, because quantum. You see, because everything here works in terms of probability waves, there's actually a small chance we can just go through the barrier and end up with a D wave, even though we don't have the energy to do that. This is an example of quantum tunneling, which you might have heard of before, and the consequence is that since we're still working with probabilities, you end up with a wave that's a mixture of S and D, which becomes more D-like as you increase the energy. This value is one of the key values we get out from our data, since it's telling us the nature of the orbital the electron was last in. Of course, so far we've only looked at atomic anions. When we move on to molecules, things get a lot trickier. All this angular distribution stuff we've just looked at breaks down because we're not looking at atomic orbitals anymore. We're looking at molecular orbitals, which are like a mix of atomic orbitals with some S, some P, some D character, and they behave very differently. Things get really complex, and we could spend a whole video on it, so we'll leave it here for now. In terms of energy levels though, they're the main focus of my research, and I think the explanations get quite intuitive and interesting. So, Make It has already explained what's going on with our electron speeds. It's the energy we put in, which is the photon energy, minus the energy required to detach the electron. We'll call that the binding energy. What actually affects the binding energy? Well, let's have a look at iodide as an example. This is actually what made the image we've been staring at for the last 15 minutes. Each electron in an atom has a unique set of quantum numbers, which tell you things like what energy level the electron's in, what orbital it's in, what the spin of the electron is, and so on. If you sort all the electrons in an atom into an arrangement with the lowest possible energy, you can say that the atom is in its ground state. So this is what it looks like for iodine. Here, each small box is an orbital, and each arrow is an electron, where the direction of the arrow tells you if it's spin up or spin down. You can see that each orbital has a maximum of 2 electrons, and always wants an up to be paired with a down. But we have one unpaired electron here. This allows for some weird behavior. The spin of an electron is intrinsic angular momentum. You can imagine it like a ball spinning on its axis, even though it's not really. But the orbital the electron's in also gives it angular momentum. You can imagine this like the ball is spinning around the nucleus, even though it's not really. These two properties can actually interact, where if one spin is aligned with the other, then the energy of our state goes down a bit. And if they're aligned opposite, then the energy goes up a bit. We call this interaction spin-orbit coupling, because you're coupling the spin with the orbit. The end result is 2 different energy levels. For negative iodide, we have 1 more electron. So all our electrons are paired up and spin-orbit coupling doesn't happen, which means we just have 1 ground state. So if we start with negative iodide and shoot our laser at it to get to neutral iodine, we can actually end up in either one of the 2 states. This means we get 2 different electron speeds. Only took us 20 minutes to actually understand exactly what's going on in this image. But something you might be asking at this point is, why do we even need to do the experiment on iodine if the energy levels are so well known? Well, for one, it's cool. But also, these energy levels in iodine are really well defined. Damn, look at that accuracy. This means we can use it for calibration. Remember how the radius of the spheres in the image related to the kinetic energy of the electrons? Well, if we want to actually get a value for our kinetic energy, we need to figure out what this unknown multiplier here is. Iodine lets us solve for it, because we already have the kinetic energy from scientific databases, and the radius is right here in the image. Finally, we can get to the actual research. I'm mainly looking at the energy levels in molecules. So what's going on in molecules? Let's imagine a molecule with 2 atoms and make a graph for the energy versus the bond length. If you start with the atoms really far apart, they're slightly attracted to each other, so the energy goes down as they get closer. If you let them keep moving closer, the force of attraction gets stronger and stronger. This is what the gradient of the slope represents. But at a certain point, they actually start to repel each other, so the energy starts going back up. This means the graph kind of functions like a ball rolling down a slope, where it can wobble around, but it wants to be at this midpoint here, which we can think of as the optimum bond length. This wobbling is basically like our atoms are joined by a spring. If we zoom in on this part of our curve and imagine there's no energy loss, then we end up with an oscillation, a harmonic oscillation. You can set the energy of the oscillation by just choosing a starting point and letting go. But because quantum, only specific energy levels are allowed, and the lowest level actually sits a bit above 0, meaning our bond can never be completely stationary and always has some energy. Each of these vibrational levels has its own wave function, which we can square to get a probability density, which just means that if we look at this level, for example, the bond length is more likely to be around here than around here. So how does this relate to our experiments? Well, the electronic states in molecules, which are these levels from before, all have their own vibrational levels. This is actually how things like fluorescence work, but that's for a different video. What we care about is how these vibrational levels behave in the photodetachment process. So let's map them onto our electronic states. We'll also ignore the higher vibrations for the negative molecule, because those aren't really occupied unless you're at high temperatures. So when photodetachment happens, like before, the photon gives us energy and we have to end up in this electronic state. But now there's a bunch of slightly different levels we could go to. So how do we choose one? When one of these transitions happens, it's so fast that there's no time for the nuclei of the atoms to actually move. This is why any arrow we draw has to be perfectly vertical here. If our anion starts at some specific bond length, then after the transition, the bond length needs to be the same. So if our anion started at this optimum bond length here, then a transition to this level is really likely, but a transition to this one is really unlikely. If you consider the entire wave function, then all you're really doing is seeing how well the initial and the final wave functions overlap. If the overlap is good, then the transition is likely, and so you get more intensity in your graph, because more electrons will be ejected at that energy. So this is what we'd expect the graph to look like. High intensity for our fastest electron, because there's really good overlap, and then you get lower and lower intensity as the overlap gets worse and worse. But hang on a minute, we've made an assumption here. We've assumed that the optimal bond length for the neutral is the same as in the anion. In reality, a lot changes when you take an electron away, so the bond length usually isn't the same. This means that in our graph, the entire electronic state shifts slightly to the side. Now if we look at the overlap, we can see that the transition to the lowest state isn't the most likely one anymore, and we'll get a different spectrum depending on how the bond length has changed. This is one of the main things I'm actually measuring in my research, looking at specific unstable molecules and figuring out the energies of these transitions, like the most intense one and the lowest one, because these tell you about how the molecules behave. Unfortunately, I can't really show examples because the molecules I'm looking at are quite unique. Okay, maybe one quick image, but I can't tell you what this is. As you can imagine, things get much more complex when we move from 2 atoms to 3 or more atoms in a molecule, because this graph is no longer 2D. So extracting all this energy information, along with all the angle stuff from before, gives a ton of insight into what the molecules are actually doing. So that's my research. Hopefully we've managed to paint a bit of a picture for how we go from putting something into a completely unknown mystery machine of death to how we actually get information about our molecules out. As you can probably tell, I find all this really interesting, but I also think it's not as complex as it seems. Of course, a huge thank you to Make It for letting me talk about electrons for 10 whole minutes and providing animations for it.
And so yeah, there we go. Thank you to my beloved patrons for supporting me. Otherwise, I would not have been able to spend 2 weeks on this video. My goodness, I'm so behind on my upload schedule. A special thanks to Acronymus, Useless, Quasar, and Lakebear for supporting me with the highest patron tier. Also, thanks to Ovo for this lovely art. And also this one, I suppose. Positron for the Valentine's Day art. It's really lovely. And obviously Stamp for spreading my propaganda. Also, in the meantime, we did a live stream where I was playing Doom Eternal, and for each death, I donated $1 to charity. It was very expensive. And there is the website, which tracks how much everyone donated to charity, which I would also recommend. I have a Discord, I have Patreon, as I mentioned. And honestly, I think that might be it. Thank you everyone so much for watching, and have a great day. Bye.
Okay, so, source stuff all comes in through here, through these valves. Goes up into the instrument in here. This is where time of flight starts. You can see there's like a long tube here for time of flight. This is all laser setup. This is our big OPO setup. Laser goes in through there, into there, does its thing, VMI up here.